Good morning, ladies and gentlemen. Welcome to our Wednesday lecture for WTW 124. We are about 7 minutes early, but in the meantime, if I could just ask those of you who are already in the audience just to confirm whether or not you can hear me okay and whether or not you can see my screen okay. Perfect. That looks like everything is functioning correctly. Then we are about 6 minutes early. We will start in about 6 minutes time. Please bear with us. Okay, good morning, ladies and gentlemen. It is 8:30 on a Wednesday, and that means that it is time for WTW 124. So just before we start, just a little bit of housekeeping. We have to choose class representatives. So you will have seen the announcement on ClickUp. So if there are any volunteers who would like to serve as class representatives for this course, by all means, please volunteer on the appropriate text channel on the Discord by introducing yourself. I will take a look a little bit later if there are any volunteers. Then, since there are no in-person tutorials this week because of the public holiday and no lecture days, do take a look at the video tutorials that were posted to YouTube that discuss some of the more difficult problems in this week's homework. Okay, and then as usual, I will do my best to keep an eye on the comments, but I must ask again, as usual, please keep your comments on topic, on the topic that we are currently discussing and relevant to what we are currently discussing. Okay, so let's begin. So last week on Friday, we introduced the cross product. So that is quite important. So, and one thing that you must remember, or two things that you must remember, is if we take the cross product of two vectors, u and v, and remember algebraic vectors, they always have their base at the origin. If we take the cross product of two vectors, we get a new vector. So remember that is different from the dot product. The cross product output is a vector. The dot product output is a scalar. Let me repeat that. The cross product output is a vector. Dot product output is a scalar. And what you should remember is that the cross product, so u cross with v, is always at 90 degrees or perpendicular to the two inputs that you give in the cross product. So u cross with v, that is a new vector, and that new vector is perpendicular to the vector u and is also perpendicular to the vector v. So this is very useful, specifically if we want, if we have two vectors and we're looking for a new vector that is perpendicular to it. So then we can just immediately compute the cross product, and that will give us a new vector that is perpendicular to the inputs. So let's take a look at an example where we will apply this. So let L1 be the line through the point P, which is 1, 1, 2, and Q, which is 2, 0, minus 1. And let L2 be the line through the points U and V. So U and V, and U is 1, 1, minus 1, and V is minus 1, 3, 3. Now we have two questions. So number A, show that L1 and L2 intersect in a single point, and let's call that point A. And number B, find a parametric equation for the line through A perpendicular to both L1 and L2. Okay. So that is our question. So here we have a line through these 2 points, a line through those 2 points. Then we have 2 questions. Show that these 2 lines intersect in a single point, and we want to find a parametric equation for the line, let's call it L3, through the point of intersection, but which is perpendicular to both L1 and L2. So just to illustrate what is going on, so we have, for example, a line like that and a line like that. These 2 lines intersect in a single point, and we're looking for, so that will be A, and we're looking for the line that goes through that point, which is perpendicular to both of these 2 lines. And it is very useful, and I will actually say, well, it's very useful and perhaps very, very important to use a computer to make a plot that you can rotate your situation around and see what is actually happening. So it's very, very useful for you to play with a tool like GeoGebra to see the situation. Okay, so let us start with our solution. So we've got L1, which is the line through P and Q. So L1 looks like this. It is the set of all points, P plus T, Q minus P, where T is a real number, and L2 is all the points U plus S, V minus U, where S is a real number. And so number A, we already know how to compute the intersections of lines. So L1 and L2 intersect in the point A, and A is 4 minus 2, 7. And that we will leave as an exercise for you. We already know how to compute the intersection of 2 lines. So please do that exercise. And now we want to answer question number B. So we want to find a parametric equation for the line. So if we look at the situation that we drew here, we're looking for a line, a parametric equation for the line L3 that is perpendicular to line 1 and line 2. So what we will do is, well, we will take the direction vectors of line 1 and line 2, and we will compute the cross product of these 2 direction vectors for line 1 and line 2, and what we will get is a new direction vector that is perpendicular to the 2 given direction vectors, and that will then be the direction vector for the line L3 that we're looking for. Okay, so let us do that. So to find a direction perpendicular to okay, and now we're looking for a direction that is perpendicular to the direction vectors of each one of these lines. So perpendicular to Q minus P, to Q minus P, and V minus U. So we take the direction vectors of the 2 lines that we have, L1 and L2, And how do we find a direction that is perpendicular? We compute. So how do we? So we find a direction perpendicular to these two vectors by computing the cross product of these two vectors. So by computing P minus Q cross with V minus U. Okay. So let's compute that. So let me move this a little bit down. P minus Q is actually, let me just make that should be notice here I just made a little mistake. Q minus P, that should be Q minus P. It actually doesn't matter. So let's just take a look. What is Q minus P? Q minus P will be 2 minus 1, which is 1, 0 minus 1, which is minus 1, minus 1 minus 2 is minus 3. So 1 minus 1 minus 3. So 1 minus 1 minus 3. Cross with, and V minus U is the vector minus 2, 2, 4. So we want to compute this cross product. So just since the cross product is still new to us, let us again demonstrate our mnemonic for computing the cross product. So what we do is we write the first vector on top, 1 minus 1 minus 3. Second vector at the bottom, minus 2, 2, 4. And now we're looking for the three components of the cross product. And remember, do not forget that we need to put a minus in the middle component. That is very important. Okay, so now we're ready to compute our cross product. So what we do for the first component is we cover up the first components and we work out the crosswise multiplication here of the two vectors. So that is going to be minus 4 minus minus 6. So minus 4 plus 6, that is 2. Okay, so now we've got our first component. Second component is that is going to be 4 minus 6. So that is going to be minus 2. And don't forget your minus in the middle component. Then our final component, cover up the final component, that is going to be 2 minus 2, so that is going to be 0. So our cross product is 2, 2, 0. Okay. Okay, there is a question from Mr. and Miss Hadebe. How do we choose which one to put on top? It's always the first one that you put on top. If you put the other one on top, you will end up with a sign error. So it's always the first one on top, second one on the bottom. Okay, so now we have a direction that is perpendicular to Q minus P and V minus U. Okay, and now we're ready. Well, we know a single point on the on the line that we're looking for. So we're looking for, let's just read again. We're looking for the line that goes through A but is perpendicular to L1 and L2. So now we have a point A, and now we have our direction computed from the cross product. So now we can just write out a parametric equation for line 3. So points X on L3 satisfy the parametric equation X is equal to A plus T Q minus P cross with V minus U, and that is for T in the real numbers. But we know what these vectors are. That is 4, minus 2, 7, that is A, plus T times, and the direction that we computed from the cross product 2 to 0, with T in the real numbers. So there we have a parametric equation for line 3. Okay, let me take a look at the comments. There is a comment about the final component in the cross product. So let's just double check, cover up the last two. So that is 2 minus 2, which is 0. So minus 2 times minus 1, which is 2. So that is 2 minus 2 is 0. So yes, that one should be 0, and I see some other people confirm that in the comments. Okay, so the point here was we can use the cross product to compute a vector that is perpendicular to, for example, here, the two direction vectors of two lines, to find a parametric equation for the line that is perpendicular to the two given lines. Okay. So let us mention a few more properties of the cross product. So these we will not prove. They might prop up later if you are doing mechanics, or if you're doing physics as well. Sometimes these properties of the cross product will pop up. So this is theorem 1.7.13. If we have algebraic vectors u and v in R3, then there is a relationship between the norm of the cross product of u and v and the dot product of u and v. So that is equal to the norm of u squared, the norm of v squared, minus with the dot product squared. Okay. And this is not very difficult to prove. All that it is a little bit of tedious algebra and using the definition of the dot product, the cross product, and the norms of vectors. And notice here we're taking the norm of the cross product. Why are we taking the norm of the cross product? Because it is a vector. So that is why we're taking the norm of the cross product. And another property of the cross product is the relationship between the magnitude of an angle and the cross product. So that is the topic of theorem 1.7.15. And this one is also very useful in physics if you're doing physics. So if we have R, U, and V in R3 with U and V not zero, and we take a look at the rays, ray 1, R plus TU, where T is a non-negative number, and ray 2, which we define as R plus TV, where T is a non-negative number. And let theta denote the magnitude of the angle. Of the angle formed by these two rays. So we've got these two rays have the same origin, so they form an angle, and now there is a relationship between the magnitude of the angle and the cross product, and the relationship is the sine of the magnitude of the angle that is equal to the length of the vector u cross with v, so the cross product of the two direction vectors of the rays divided by the lengths of these direction vectors. So it looks almost like the definition of the magnitude of the angle, except we take the norm of the cross product, and instead of the cosine, we take the sine. So that is the relationship between the magnitude of an angle and the cross product. And we will not prove this, but it is useful for us to note that this is actually true. And again, let me reiterate, if you're doing physics, then it is likely that you will encounter this identity somewhere in physics. Okay. So now we will take a look, or we will return to planes, and we will take a look at a different way of representing planes. And this different way, well, we've already seen one way that we can represent points on a plane. That is through a parametric equation for a plane. Now we will look at a different way, and this different way is called a Cartesian equation for a plane. So let's take a look at theorem. This is theorem 1.7.16. So we let n be a vector, and we let r be a vector in R3, and we make sure that n is not 0. Then the set, so the following set, all the points x in R3 that satisfy the following equation. So n dot with x minus r equal to 0. This set is actually a plane, and this plane actually contains the point R. Okay, so here we have a different way of describing planes. Okay, and we will now discuss this different way of describing planes. So let's take a look at theorem 1.7.17. So the first question we should have, if we have a parametric equation for a plane, how can we describe the plane in this different form? So that is the topic of theorem 1.7.17. So let P, Q, and R be in R3 with P minus R and Q minus R not scalar multiples of each other. Then we have that a point in R3 is an element of the plane, so is on the plane, the plane through P, Q, and R. Let's write out what that set is. That is the set R plus S, P minus R plus T, Q minus R, with S and T real numbers. So a point, X is on the plane. That happens if and only if we have that this point X satisfies the following equation. So N dot with X minus R is equal to 0. And what is this N? This N is defined as being perpendicular to these two direction vectors for the plane, P minus R and Q minus R. But we know how to compute a vector that is perpendicular to both of these vectors. That is the cross product. So P minus R cross with Q minus R. Okay. So here we now show how can we translate between, for example, a parametric description of a plane and a Cartesian description of the plane. Now there are a couple of remarks that we should make. So let us call this equation number 1. So remarks. So this equation number 1 that we have here, this equation underlined in red here, that equation is called a Cartesian equation. For the plane P. Okay. And Cartesian comes, that is in honor of the philosopher and mathematician Descartes. Okay, so that is the first remark. Second remark is this vector n has a special name. It is called a normal vector for the plane P. So the vector n is called a normal vector. For the plane P. Okay, and very often we write this equation number 1 that we have here, this equation, we write that in a little bit of a different form. So the third remark that we make is we often write with our point x having coordinates x, y, z, and our normal vector having components n1, n2, n3. We often write equation 1 as follows. So we what we do is we compute the dot product, so that is going to be n1 plus n1 times x plus n2 times y plus n3 times z, and with n dot with r on the other side. So if we take a look at this equation, use the properties of the dot product, so n dot with x here, that is what we have on the left here, and we take the minus n dot with r, we take it across to the other side, and that is how we get our n dot with r on the other side over there. And so you will very often see equations for planes in this form. Okay. So before we continue, let's just think a little bit about the intuition. What is going on here? So let's think about the intuition. So let's take, for example, a vector n which has coordinates 1, 1, 1. And let us think about what the set of all points in R3 look like, which satisfy the following equation. N dot with x is equal to 0. So notice here this is not a full general Cartesian equation, but this is just for illustration purposes. We're missing a vector r in here, but let's just think about what happens here. So let's think about what's going on here. So this vector n has coordinates 1, 1, 1. So it kind of looks like that. And if you think about exactly what its coordinates will be, that will be 1, 1, and 1. And now, let us think about the interpretation of this equation here. What does that mean? So remember, from the definition, the magnitude of the angle, if we have the dot product of two vectors being 0, we should immediately remember that that means that these two vectors are at right angles to each other. So n and x are at right angles to each other. So in other words, this set is the set of all the points which are at right angles, or of all the vectors which are at right angles to this vector n. So what we get is all possible vectors which are at right angles to this vector n. And if we put all of them together, what we get is a plane. And this plane is at right angles to this vector n. And that is why this vector n is called a normal vector to the plane. Because this normal vector, normal meaning is kind of a standard word in mathematics and in physics, meaning at right angles. So this vector n is normal to the plane, meaning it is at right angles to the plane. However, this plane always goes through the origin. So, for example, if you have another vector, let's say n points in which direction, like that. So if that is the vector n, then the plane which is normal to n kind of looks like that, but it still goes through the origin. Okay. However, we know that not all planes go through the origin. You can easily devise an example of a plane which does not contain the origin or does not go through the origin. So that is why where did we have that? That is why we have this r in here in a Cartesian equation for the plane, because that allows us to shift our plane. So it is just like, or it's very similar to what you will have done at school, shifting the graphs of certain functions that you plotted. Okay, so let us discuss that. So if we take a look at the following set, so n is not 0, and we have r in R3. If we look at the following set, all the points x in R3, which satisfy the following equation, and now the full Cartesian equation, x minus r is equal to 0. Let us think about how, let's say, the intuition between, the intuition of understanding what this set looks like. So we've got our vector n, and we've got now our point r there. So what this set looks like is it is all the points, but now translated so that this point r is actually in the plane. And if you kind of detach this algebraic vector n and you move it to that point r, what you will see is that all the points on the plane will be at 90 degrees to that vector that you detached. So, but also just be careful. Remember, algebraic vectors always have their basis at the origin. Okay, so this is what this minus r does. It translates a plane to force it to have the point r to actually be on the plane. So if we, for example, if we didn't have this part, we would have a plane going through the origin that is at 90 degrees to n. So if we add this minus r, what happens is this whole plane, hopefully I've grabbed all the parts of the plane. Let me redo that. That should be like so. So if we add this minus r, has the effect of translating this plane so that r is actually part of the plane. And if we move our normal vector to that point, we will see that that normal vector is still at 90 degrees to the plane. So that is roughly the intuition behind the Cartesian or a Cartesian equation for a plane. So remember, R is a point on the plane, any point on the plane, any single point on the plane, and N is a normal vector of the plane. Okay, let me just take a look at the comments, if there are any comments that I should address in the chat. No, does not look like it. Okay, so now we have two questions that we need to answer. We have now two different ways of describing a plane. So one question is, how do we move between the two different representations of a plane? How do we move between a parametric equation for a plane and a Cartesian equation? Question mark. So how do we do that? And secondly, why do we need Cartesian equations for planes? So these are two questions. So the first question is, of course, that is a bit that is technical. So that is a question about technique. The second question is a little bit more fundamental. What is it good for? Why do we need these two different representations of planes? So the astute among you will have noticed we've not discussed yet how to compute for example, the intersection of two planes. Why did we not do that yet? That is because we did not have the correct tools yet, meaning we did not have Cartesian equations for planes yet. You can try to compute the intersection of two planes using their parametric equations, but then you have to solve, if you think about it, then you have to solve for 4 variables. So you've got 2 parameters for the one plane and 2 parameters for the other plane. So you have to set up an equation and then you have to solve this equation for 4 variables. And that becomes a little bit cumbersome. So if we use Cartesian equations for planes, then that becomes a little bit easier. So that is one reason why we need Cartesian equations. Okay, so let us now discuss this first question. How do we translate, or how do we move between a parametric equation and a Cartesian equation for a plane? So if we have a parametric equation, how do we find a Cartesian equation for a plane? If we have a Cartesian equation for a plane, how do we find a parametric equation? So let's take a look at an example. So let P be the vector 1, 2, minus 1, Q be the vector 2, 1, 0, and R be the vector 1, minus 1, 1. Then question is, find a Cartesian equation for the plane through P, Q, and R. Okay. So we can write down what our plane is. Well, the plane through P, Q, and R is the following set. Well, it's the set all points R plus T, P minus R plus S, Q minus R, where S and T are real numbers. Okay, and now what do we need to write down a Cartesian equation? We need a normal vector. And what do? We take the two direction vectors of our plane and we work out a vector that is perpendicular to both of them. And now it's very lucky we know how to do that because the cross product gives us a vector that is perpendicular to both of them. So we define n to be the vector P minus R cross with Q minus R. Okay, and that is 0, 3, minus 2 cross with 1, 2, minus 1. And when we work that out, what we get is 1, minus 2, minus 3. And now we can write down a Cartesian equation for P. For P is the following. That is n dot with x minus r. And what r is this? This is, of course, this r. And that is equal to 0. So if we expand everything, if we expand with x having components x, y, and z, we obtain the following. We obtain x minus 2, y minus 3z is equal to 0. And where does this come from? Well, that is, of course, n dot with x, and this 0, that is what we get from n dot with r. So what we do is we expand the left-hand side of our Cartesian equation and we take the n dot r across. Okay. So here we have a Cartesian equation for our plane P. And we can always check. So we can always check our answer by substituting P, Q, and R. So substitute the coordinates for P, Q, and R into our Cartesian equation. So for example, for P is what? That is 1, 2, minus 1. And now we can check by substituting these coordinates into our Cartesian equation. So that has to be 1 minus 2 times 2 minus 3 times minus 1. If we work that out, that is going to be 1 minus 2 plus 3. 1 minus 4 plus 3, and that is equal to 0. And that is exactly what we need on the right-hand side. Okay, and we can also check that Q and R satisfy our Cartesian equation. Okay, let me just take a look at the comments. There's a question in the comments. How do you invert from a Cartesian equation to a parametric equation? That is coming, but unfortunately not today because we are out of time. So today is Wednesday, tomorrow we don't have any lectures, so that question will be discussed on Friday. Okay, and with that we are out of time. So today is a Wednesday. I wish you all a very lovely Wednesday. I will see you in our lecture on Friday. Have a good Wednesday, everyone. Goodbye.